Hi, welcome to the video. So let us now solve this problem. Consider a 5-meter high, 8-meter long, and 0.22 thick wall whose representative cross-section is as given in the figure. So we have here this figure. So let's analyze our problem. Say we have this from the figure. Here is our 8-meter long, and our thickness is about 5 plus 10 plus 6 is 21 cm plus 1. We have 22 cm or equal to 0.22 meter, right? While our height is 6 cm plus 6 cm is 12 cm or 0.12 meter, okay? But as you can see here in our given problem, it says a of 5-meter high. So I think there's something's wrong in our given. So instead of using this 5-meter high, let's use the given value in our figure. Say this is our figure 1. So let's follow this figure instead, okay? So our height now is equivalent to 6 plus 6 is 0.12 meter or just a 12 cm high, okay? So consider this cross section. Determine conductivities of various material used. So as you can see here in the figure, or in figure 1, we have a composition of different materials A, B, C, D, E, and F. So those materials have different thermal conductivities, wherein our material A has 2 watts per meter Kelvin, which is also equal to the thermal conductivity of the material F. So A and F is equal to 2. Our material B is 8. So here is our material B, located between the material C. So our material C has 20 thermal conductivity, while our material D has 15. E is equal to 35. Okay, so the left and the right surfaces of the wall are maintained at uniform temperatures of 300 degrees C and 100 degrees C, respectively. So say this is our 300 degrees C. Say let's call this at our point 1, and the in between this wall, say this is our point 2, and between these walls, say this is our point 3, point 4, and point 5. Okay, so the left temperature is at 300 degrees C, which is at our point 1, and the right surface wall are maintained at 100 degrees C, which is at our point 5. Okay, assuming the heat transfer through the wall to be one-dimensional, so determine the following. So we need to determine these 3. Okay. The rate of heat transfer through the wall, so we have to determine the Q from this side up to this side, from point 1 to point 5. Then, since our higher temperature is from this side, from point 1, so the direction of our flow is from point 1 to point 5. And B, the temperatures at the point where the sections B, this is our material B, D and E meet. So we need to determine the temperature where the section B, D, and E meet, and that is at our point 3, right? So this is our B, D, and E. So at this, So at this section, what is the temperature? Okay, so at point 3, and determine the temperature drop across the section F. So this is our F, and we need to determine the delta T from point 4 to 5, and that is across F. Okay. Before we proceed to the computation of this 3, let's first list down necessary information. So list down necessary info. So those informations are regarding, since we have the illustrations here for the different measurements, we can now list down the thermal conductivities of these materials. So thermal conductivity of A is equal to 2. B is equal to 8. C is equal to 20. D is equal to 15. Conductivity of material E is 35. And since A and F is equal to 2, then our material F is also 2, because A and F is just equal to 2. Okay. After listing down necessary informations, we can now proceed to our A, which is we need to determine the rate of heat transfer through the wall. Okay, so in order for us to solve for the heat transfer through the wall from point 1 to point 2, okay, we can now use the formula Q is equal to delta T all over the overall resistance, thermal resistance of these walls. Okay, we're in our delta T here. If we analyze this, our delta T here, delta T is just equal to, since this is our figure, our delta T is P1, temperature at point 1, and temperature at point 5. So we have T1 minus T5. So we have 300 minus 100. So we have 300 minus 100, and it is equal to 200 degrees C. Okay. While our total R